Hey kiddos, happy week 25. Today we're going to apply our understanding of diffraction and interference to modeling interference patterns for waves diffracted through one slit, two slits, and many slits. Right, it's been a while since we've talked about properties of waves because we've been doing our IAs, so it might be worthwhile going back and doing a little bit of review from the last couple lessons before we split off to do our IAs. Okay, remember, of the things that waves can do, right, if something is acting like a wave, it can reflect, refract, diffract, and interfere. Okay, so far we've been talking about interference and diffraction. Right, diffraction is just bending of a wave around an obstacle, and interference is when different points of a wave overlap and make a pattern. We will in this unit also talk about patterns in reflection and refraction. I know some of you did your IAs on reflection and refraction, and we will take a look at those still in this unit. Okay, if you have not already done so, please also take my end of the school year survey. We've got a little bit of flexibility in the end of our school year because we won't be taking the IB exams, and so I want your feedback on what we study after we finish our Waves of Light unit. All right. So here's a diagram, if you remember this from our ripple tank simulation. This shows an interference pattern produced by two sources that oscillate on the surface of a liquid. So we've got our 2 point sources right here. Right, those are our two disturbances, and we're seeing those waves propagate, but also the waves from those two sources are overlapping and interfering. Okay. What we noticed when we were observing this is that when looking in three-dimensional space, these lines here were minima, right? There is no amplitude here, so that those must have been regions of destructive interference. Okay, let's do a better job with that one. Okay, and so my question is, and so you're getting these high amplitude parts where the waves can oscillate normally, and then there are these predictable regions where there is just no amplitude. There's completely destructive interference. So my question is, which of the distances shown in the diagram corresponds to one fringe width? The fringe width is the width of one like high amplitude spot, or one, if this is light, it would be the width of one bright spot. Okay, so the width of one, we're not talking about wavelength, we're talking about the width of one high amplitude region. And so the width of one high amplitude region, or one fringe width, would be C. One fringe width is the distance from minimum, right? A minima is like a spot with minimum amplitude, one of those regions of destructive interference, to the very next minimum. Okay, so we call that a fringe width. From one minimum to the next. Okay. All right, now in class, we took a look at this example that we did the last time that we met. It was with two speakers connected to the same sound source. Okay, two speakers connected to the same sound source. Two speakers. All right. And those sound sources were 3.2 meters away. Each of them was 1.6 meters from their midpoint. And that line from their midpoint directly over to a set of probably microphones or something picking up the sound, right? A screen of some sort, was 4 meters. Again, this is not to scale. If the wavelength of the sound that those two speakers are emitting is 1.1 millimeters, we want to know if you would get constructive interference here and or constructive interference here. And in class, I asked you to go back and review that problem. And I would like you to do that right now as well. Go back to your notes and review our solution to this problem. Okay, let's look at point O. We use the Pythagorean theorem to figure out the length of the path that the wave travels from point Y to point O, and then from point X to point O. So the path length, right, in a straight line from the sound source to where the sound would be received is 4.308 meters for both of them, right, because they're traveling the same distance. 4.308 meters. So at point O, the path length difference was 0. And since both of the speakers were emitting the same sound at the same time from the same source, their sound was considered coherent, right? Coming out of both speakers at the same time would be a crest, at the same time a trough would be released, right? They were exactly synced up, right? So as they travel, those exact waves travel from those two sources the same amount of distance. The maxima and the minima would be lining up with each other, right? If the path length difference is 0, then we would get constructive interference. Right. This is sound wave, so we'd hear a loud sound at that point. If we were talking about light, we would see a markedly bright spot. All right, now let's take a look at point P. Okay, doing a little trig, which I know you can do. As a reminder, from point Y to point P was 4.089 meters. And from point X to point P was 4.639 meters. Okay, the path length difference, the difference in the distances that the waves travel to get to point P, is literally like subtract those distances. 4.639 minus 4.089, and you get a path length difference of 0.55 meters. Okay, how does that compare to the wavelength of 1.1 meters? It's exactly half. So what that means is if we had one wave like this, that would mean, oops, the two waves were exactly off by half of a wavelength. Would be the path length difference. And what happens when those two wavelengths are off by, two waves are off by half of a wavelength? We get max aligned with a min, and we get cancellation. So this is destructive interference. Okay, so we talked about for constructive interference, the path length difference had to be 0 or 1 wavelength, 2 wavelengths, right? An integer number of wavelengths. Destructive interference, the path length difference had to be an integer plus 1/2 number of wavelengths. So half a wavelength, 1.5 wavelengths, 2.5 wavelengths in order for there to be destructive interference. So this is an important reminder about what we've been talking about so that we can now have that same conversation about light. Okay, so we took a look at waves in our ripple tank simulation from a couple of weeks ago. We talked about a couple of things. We talked about how single slits or obstacles with a single hole in them produce kind of a circular waveform, right? Waves come through the slit and they produce, coming through the slit, right, little waveforms on the edge. And those waves interact with each other, right, to produce an interference pattern. Okay. We also talked about Huygens' principle, saying that when you've got a wave front, those wave fronts are created by individual wavelets, right? There are infinite number of little wavelets, and each of those little wavelets create a disturbance in the medium, and they all kind of overlap to create a wave front, right? But at the edge, there's nothing on the top or the bottom to cancel them out, or smooth out the little wavelets. And so that's why on the edges, you get these circular looking disturbances, which seem as though the edges of the single slit act as point sources.